Hi. So for the lab 3 of physics 2, we will be talking about circuits. And so for this lab, we'll start with the purpose. So the purpose was to predict circuit behavior with series and parallel resistors, measure current potential with multimeters, and explore resistor and capacitor behavior. So in this experiment, the system and surroundings, the system was the circuit and the surroundings was basically everything else. And so the results showed that current in an RC circuit is time dependent, and node and loop rule hold true. So to start off, we'll talk about a few fundamental physics principles, which are the node rule, which states that current flowing into a node, which is shown here, is equal to the current flowing out of it, which is here. And that is the result of charge conservation. And so it's the same thing up here, and this is the loop rule, which is the sum of all the electric potential differences around a loop is 0, which is also a result of energy conservation. So as you can see, the sum of all of these is equal to 0. And lastly, we'll have Ohm's law, which is current through a conductor between 2 points is directly proportional to the voltage across the 2 points, and that is shown in V equals IR. So then we'll talk about charge and energy conservation in series circuits. So we assumed when we were making this that current is the same everywhere in the series. And so the goal of this was to predict the currents I1 and I2 that would be measured by the 2 ammeters. And so when we put this circuit together in real life, we predicted that it would be 0.0204 amps for both I1 and I2. And when we actually did it, we got 0.017 amps, which is similar, not exactly, because the batteries could be not as fully charged, there's resistance that we didn't account for in the wires. And so if we did the reverse connection to the ammeters, that would just flip the signs of the ampage. So now we're going to replace the ammeter with a voltmeter. And so the ammeter reads 0 volts over here because the voltmeter has extremely high resistance. So there's no more current flowing after the voltmeter. And the voltmeter reads 2.6 volts since there's no other voltage drop. And that's not exactly 3 volts because these batteries could not be fully charged and there could be a voltage drop in this. And now we look at the voltage drop across the entire circuit. And so the potential difference across the circuit elements, we have 0.8 volts across here, 1.7 volts across here, and negative 2.6 volts from here to here, all the way around the circuit. And so we measure the total voltage to be negative 0.1 volts, and theoretically it should be 0, but this could just be rounding or experimental errors. And then we graphed it here, so you can see it goes up with the batteries and then comes down as each resistor goes. And so now we put an ammeter across the 100 ohm resistor, as seen here. So they're in parallel. And since ammeter has very low resistance, the current will go through the ammeter instead of the 100 ohm resistor. So that brings the total resistance down to 47 ohms. And so the current through the ammeter spikes to 0.043 amps. And so the results of this show that through the 47 ohm resistor, we have 43 ohms. And that's because, and for the 100 ohm resistor, we have 92 ohms. And that's because these aren't exactly perfect. And our measuring tools are slightly off, but they're pretty similar. And the wires should have 0, the wires and the ammeters should have 0 ohm resistance as well. And so now we'll go into the RC circuit. And in this circuit, we did a circuit with a 10 ohm light bulb and a 20 ohm light bulb. So with the 10 ohm light bulb, it took approximately 10 seconds to charge and 10 seconds to discharge. And with the 20 ohm light bulb, it took approximately 20 seconds to charge and 20 seconds to discharge. And both circuits have the light bulbs start really bright, and they slowly dim as the capacitor discharges. And so here's a graph of our RC circuit. And as you can see, the predicted RC which is tau, is equal to 10 seconds. And the experimental RC that we found is equal to 8.453 seconds. So a little off, but still just experimental error and human error. And so, as I've been talking about throughout this whole lab, we'll talk a little bit about the errors. So we have the human error in stopping the stopwatch at end capacitor from discharging at the exact same time, which is an error. And then another error we have is the resistance in the wires that we accounted 0 resistance for is not actually 0. And same with the ammeter, and yeah, other stuff like that. And also the batteries may not have been fully charged, so they might have not gotten the predicted amount. So for the discussion, we'll talk about what if you charged a capacitor with no resistance in the circuit. And if there was no resistor, the capacitor would charge instantaneously, but that is all theoretical. In reality, no circuit is truly resistor-free. Wires, batteries, and even the capacitor itself has internal resistance. And so that is why if we don't have a resistor, like the circuit still has resistance, so it's not going to charge instantaneously. So thank you so much for listening.